Hey there, welcome to Night Lectures, your daily dose of fascinating stories. The name of Archimedes is known to every schoolchild. But who was he really? This man who ran out of the bath and shouted, "Eureka!" In this video, you will learn how a boy from distant Sicily became the greatest mind of the ancient world, how he discovered a law that is still studied in every school, what kinds of machines he built to stop the Roman army, and why the Romans feared not his soldiers but his mind, how his final moment looked, and why his death became a legend. You will discover why Archimedes was not just a scientist, but a man who tried to understand the very essence of the world, and he left behind puzzles that we are still solving today. Share your ideas for future videos in the comments and hit the subscribe button. New bedtime stories come out here daily. Syracuse in those times was not just a city. It was a major center of Greek culture outside the Greek mainland, a prosperous state on the island of Sicily, surrounded by walls and the sea, with bustling markets, theaters, temples, and a harbor where merchants from all over the Mediterranean would dock. The city was independent but often balanced between alliances, wars, and diplomacy. Italian and Greek influences mixed here, and into this environment Archimedes was born. The exact date of his birth is still debated, but most often the year 287 before Christ is named. His family belonged to a respected circle of educated citizens. Archimedes' father, Phidias, was an astronomer. He left no writings, but according to Archimedes himself, it was his father who first awakened in him an interest in numbers, stars, and their movement. It is likely that Phidias engaged not only in observing the heavens but also in practical calculations, calendars, predictions of eclipses, and computations for navigation. All this knowledge was passed from father to son, not in the form of formal lessons, but as part of life, through conversations at dinner, shared observations on the rooftop, and debates with other scholars. Education in Syracuse began with elementary training, reading, writing, the basics of Homer and Hesiod's poetry, and geometry. But Archimedes quickly stood out. He did not just memorize, he asked questions. Why does a star move? Why does a circle always relate to its diameter in the same way? Why does water flow downward and not sideways? Servants said he could sit on the floor for entire days, drawing lines in the sand and counting to himself. Yet a boy alone, even with natural talent, would not have become Archimedes without his environment. Syracuse at that time was one of the centers of Hellenistic science. After the campaigns of Alexander the Great, much new knowledge spread from Egypt, Mesopotamia, and Persia. Scholars, philosophers, and engineers lived and worked in Syracuse. At the court of the Syracusan ruler, Hiero II, debates were often held, lectures were read, and discussions about the structure of the world took place. Hiero, who would later become Archimedes' patron, was just consolidating his power at this time. He was a pragmatic man, interested in utility, especially in how science could strengthen his city. He likely knew of the youth with a talent for geometry and calculation, but for now, this was only a quiet boy, lost in thought, always carrying a little drawing tablet. Sources claim that already in youth, Archimedes began deriving theorems on his own, based on the works of Euclid. He did not simply read books, he challenged himself to prove everything independently, without looking at the solutions. If he failed, he would not eat or sleep until he found the way. It was not mere stubbornness, rather an inner need to understand the essence, to reach the foundation of every truth. But life was not only about science. Syracuse was a maritime city, and boys learned to swim, to handle boats, to throw spears, and to run across rocky paths. Archimedes was not strong, but from early years he was fascinated by mechanisms, how a pulley works, how a sail holds, why a ship does not sink. These questions would later lead him to discoveries, but already then, he was said to dismantle toys and rebuild them in new ways, searching for balance, trying to understand how things worked. It is believed that in these years Archimedes formed what later became the basis of his method. He did not separate mathematics from life. For him, formulas were not abstractions, but reflections of reality. He did not just calculate. He tried to feel how a body moves, how a force acts, how a liquid flows. His first notes, sketches, and attempts at proofs were probably made in Syracuse, but soon it became clear that local teachers were no longer enough. Archimedes needed not just teaching, but a challenge. And so, when he turned about 20 years old, his family, perhaps even Hero himself, sent him to the place where the greatest minds of the Hellenistic world gathered, Alexandria. But that will be another chapter. For now, in Syracuse lived a young man who loved above all else to draw circles, measure stars, and ask questions no one yet had answers to. By the beginning of the 3rd century before Christ, Alexandria had already become the main intellectual center of the Mediterranean. Here, on the Egyptian coast, the Ptolemies ordered the construction of libraries, observatories, laboratories, and schools such as the Greek world had never known. The magnificent Mausion, the House of the Muses, gathered philosophers, astronomers, mathematicians, and physicians under one roof. To this place came those who sought knowledge, and those who were already transforming science. Archimedes arrived in Alexandria in his early 20s, not as a tourist or observer, but as a student who wished to stand alongside the best minds of his time. He belonged to the generation that continued the traditions of Euclid. Euclid himself, the author of the Elements, was already dead, but his students still taught in Alexandria. From them, Archimedes received his first systematic training in geometry. But according to accounts, he was never satisfied with explanations. If he was given a theorem, he wanted to know where it came from, how it related to others, and what would happen if one condition were changed. This approach did not always please his teachers, but it was precisely how Archimedes built his own system of thinking. One of his brightest acquaintances in Alexandria was Eratosthenes, the man who entered history as the first to measure the circumference of the earth. He was a philosopher, mathematician, geographer, and poet. Between him and Archimedes, a friendly and professional relationship grew. They continued their correspondence later, when Archimedes returned to Syracuse. Eratosthenes was older, but saw in Archimedes an equal. Their debates covered not only mathematics, but also the structure of the world, how to measure distances, whether one could calculate the curvature of the surface, whether geometry could be joined with physics. Some sources claim it was Eratosthenes who pushed Archimedes toward the idea that mathematics is not just figures in the sand. It is a tool for understanding nature, a way to measure flow, to model movement, to describe force. Within the Mausion, Archimedes began creating not only proofs, but models. He sketched. He imagined objects rotating in space, trying to see how they behaved under various forces. Later, he would do the same in his writings, thought experiments preceding mathematical exposition. It is thought that in Alexandria, he first saw the hydraulic screw, a device for lifting water that he would later improve. He may also have met the works of Hero, or even Egyptian engineers who built irrigation systems. For Archimedes, this was important. He did not isolate himself in theory. He needed to see how an idea worked in reality. In Alexandria, there was a cult of knowledge. The library, which was said to contain hundreds of thousands of scrolls, became for Archimedes a temple. He did not just read. He copied, he compared, he extracted. And above all, he drew conclusions. Many of the mathematical problems he would later work on, approximating the area under a curve, determining the center of gravity, measuring volumes, began here. In the lecture halls where the works of Democritus and Pythagoras were discussed, he learned not to repeat, but to discover. Archimedes quickly became a notable figure among the scholars. He was respected not only for his intellect, but also for his style of thought, strict, almost ascetic. He avoided rhetoric and did not join debates for the beauty of speech. What mattered to him were precision, logic, and structure. He built proofs the way engineers build bridges, layer by layer, until something solid and clear emerged. Some of Archimedes' future works, especially on the sphere and cylinder, on the equilibrium of planes, and the method of mechanical theorems, were laid down in this period. He tested their ideas with colleagues, searched for mistakes, looked for alternative paths. He understood that even if he failed to find a final solution, the very search enriched knowledge. But there was another trait of Archimedes that was noticed with irony in Alexandria. He was indifferent to fame. Unlike others who sought recognition and titles, he often worked alone, refusing food if absorbed in thought. Teachers tried to involve him in academic life, to grant him honors and positions. Archimedes refused. He cared only about knowledge itself. When his studies drew to an end, his friends tried to keep him in Alexandria. But Archimedes decided to return to Syracuse, He knew his native city was not only his birthplace, but also a field for applying ideas. There ruled Hero, whom he had known since youth. Their ships were built, trade and defense developed. There his thoughts could turn into action. And so he left, without ceremonies, without speeches. Simply, as a man who had finished his studies and was ready to begin his work. Thus ended the years of apprenticeship in Alexandria, and began the life of Archimedes as an independent scientist, inventor, and thinker, in the city to which he returned, to become its pillar in times of greatest trials. Returning to Syracuse, Archimedes did not seek political career or honors. He immediately began working, not in a school, not in a temple, but in his own workshop, where he could devote himself to what interested him most, solving problems posed by life itself. One such problem was to test the honesty of a craftsman who had made a golden crown for King Hiero II. The story has reached us through the Roman writer Vitruvius, and although some details may have been embellished, the essence remains reliable. Hiero ordered a crown to be made of pure gold. When the work was completed, its weight matched the amount of gold delivered. Yet the king suspected that some of the metal had been replaced with silver, less precious but lighter. He did not want a public scandal, but wished to know the truth, and he turned to Archimedes. The task before the scientist was difficult. He could not damage the crown, melt it, or directly analyze its composition. He needed to determine its material without destroying its form. He sought a way to measure density, the ratio of mass to volume. The mass was known. The problem was to find the volume. The solution came unexpectedly. According to legend, Archimedes entered a public bath, and upon immersing himself noticed how water overflowed. It was an ordinary sight, but in that instant he saw a principle. If an object displaces a volume of water equal to its own, then one can measure the volume of a body by immersing it in liquid, and knowing both volume and mass, calculate density. The tale says Archimedes leapt up and without waiting to finish bathing ran through the streets of Syracuse shouting, "Eureka!" In Greek, "I have found it." It was not only a moment of joy. It was the passage from observation to universal principle. He conducted the experiment, weighing the crown in air and in water, then doing the same with a piece of pure gold of equal mass. The difference in displaced water showed that their volumes were unequal, and therefore their densities as well. The crown was indeed not of pure gold. The fraud was proven, not by force or threats, but by knowledge. This case became the starting point of one of the fundamental laws of physics. What we now call Archimedes' principle is formulated thus. Every body submerged in a liquid is acted upon by an upward force equal to the weight of the liquid it displaces. The importance of the discovery lay not only in detecting a forgery. Archimedes had revealed a principle describing how bodies behave in fluids. On this basis, ships float, dams stand, and balloons rise. He explained why a massive stone sinks but a wooden raft floats, why an iron ship does not go to the bottom, because it displaces enough water. Later, Archimedes fully set out this principle in his treatise on floating bodies. There he not only formalized the law, but also examined shapes, densities, and conditions of equilibrium. He showed how center of gravity, density, and form affect stability in liquid. These works advanced hydrostatics centuries ahead. Curiously, Archimedes himself did not consider this episode the most important of his life. For him, it was a particular application of mathematics to a practical problem. Yet it became the most famous case, for it showed what made Archimedes unique: the ability to see in the ordinary a law, in the everyday a formula, in the physical a mathematical description. The crown story revealed not only the power of scientific thought, but also how knowledge could serve justice. The king got his answer without torture or suspicion. The craftsman was exposed without interrogation. It was the victory of intellect over deceit, and the first famous case where science resolved a civic issue. After this, Archimedes in Syracuse became not just a scholar, but an authority. People turned to him for all manner of problems, from water supply systems to construction calculations. He did not seek power, but power sought him. He did not chase influence, but he was listened to. For behind his ideas stood not words, but proof. The story of the cry Eureka has remained a symbol of inspiration, of sudden insight, of genius illumination. Yet behind that moment lay years of study, observation, analytical thought, and deep knowledge of nature. Archimedes had not merely found an answer. He had opened a new path to understanding the world. Archimedes entered history not only as a mathematician and philosopher, but also as an engineer, a man who could turn abstract ideas into concrete mechanisms. Unlike many theorists of his time, he did not disdain practice. On the contrary, he sought in it confirmation of his calculations. His workshop in Syracuse resembled not a study but a laboratory. Models were built there, experiments were conducted, forces, angles, and levers were tested. Many of his inventions were driven by the needs of the city, and some by the military threats that soon became reality. One of his earliest devices was the Archimedean screw, an inclined spiral inside a cylinder designed to raise water. It is believed that Archimedes saw a prototype of such a mechanism in Egypt, where similar constructions were used to irrigate fields. He improved the design, calculated its parameters, and made it suitable for wide use. In Syracuse, this screw was used to drain mines, supply water to gardens, and even pump water from lower levels into reservoirs on the fortress walls. Another invention was a system of pulleys and blocks, which Archimedes described in his works on equilibrium. He proved that with a system of levers and pulleys, a person can lift a weight many times greater than his own. It was then, according to tradition, that he pronounced, "Give me a place to stand, and I will move the earth." This was not a joke. It was a precise expression of the power of the mathematical approach to mechanics. But Archimedes' true engineering fame came later, when a threat appeared on the horizon: Rome. In the 3rd century before Christ, Syracuse found itself between two fires. At first it was an ally of Carthage, then it tried to pass to the Roman side, but ended up trapped. After the death of Hero II, his successors made a political mistake, and in the year 214 before Christ, Rome began the siege of Syracuse. The city seemed to have almost no chance. The besieging army was numerous, the fleet stood off the shore, the walls were in danger. But Syracuse had one advantage: Archimedes. He became the chief strategist of the city's defense, not in the sense of giving orders, but in the sense of ideas. He turned science into a weapon. According to ancient authors, Archimedes built a whole series of war machines: catapults, ballistae, hurling mechanisms, and devices for wrecking ships. He calculated range, angle of flight, and drawing force with precision. The Romans were stunned. Their projectiles fell short of the walls, while the Syracusan stones struck true and far. Archimedes even devised machines with variable reach. They could strike near and distant targets simply by changing the positions of the levers. Most famous became the device with hooks and cranes that later received the name Archimedes' Iron Hand. It lifted the prows of Roman ships straight out of the water, rocked them, and dropped them back, causing panic on the decks. Some historians doubt the complete accuracy of these accounts, but ancient sources agree on one point: the defense of Syracuse was not merely steadfast, it was terrifyingly precise. Another legendary development was Archimedes' mirrors. According to descriptions, he designed a system of polished bronze shields or mirrors that focused sunlight on the sails and wooden parts of Roman ships, igniting them. Modern scholars dispute whether this could be realized in battle conditions, but the idea reveals the direction of Archimedes' thought. He tried to harness not only iron and stone, but also light, heat, and geometry. These machines were not clumsy monsters. They were carefully thought-out constructions made with the laws of physics in mind. Every device of Archimedes rested on calculation: moment of force, center of gravity, distribution of pressure. He did not invent blindly. He computed, modeled, built. His mechanisms could look simple, but behind their operation stood deep theory. The Romans were bewildered. Their troops could not approach the walls. Their ships could not reach the shore. Soldiers began to believe that a sorcerer, not a man, was at work in the city. The consul Marcellus, commander of the siege, is said to have exclaimed, "Give me 100 Archimedeses and I will conquer the whole world." He understood that he was facing not just one man, but science pressed into the service of defense. The siege dragged on for 2 years, and all that time Archimedes' mechanisms kept the Romans from advancing. His engineering solutions allowed Syracuse to hold out far longer than expected. Archimedes became living proof that knowledge can be stronger than weapons and reason sturdier than walls. And although Syracuse ultimately fell, Archimedes left a legacy that outlived walls, ships, and armies. His machines became prototypes for future engineers. His calculations formed the foundations of mechanics. His name entered the roll of those who managed to place human thought between a city and destruction. In this chapter, Archimedes is not a philosopher and not a theorist. He is an engineer, a defender, an inventor, a man who showed that a true mind needs no title to change the course of history. When today we speak of Archimedes as a great inventor or engineer, we often forget that he considered himself first and foremost a mathematician. Not a general, not a craftsman, not a prophet, but a man dealing with pure forms and the laws that underlie them. His writings on geometry, arithmetic, and mechanics laid the groundwork for everything that later would be called mathematical analysis, integral calculus, and physics in its rigorous form. He lived in a world where the infinitesimal was not yet a concept and the infinite was treated philosophically, yet Archimedes began to conceive both extremes as objects of exact calculation. One of his most famous works studied the relationship between the volume and surface area of the sphere and the cylinder. He proved that the volume of a sphere is 2/3 of the volume of the circumscribed cylinder around it, including the base and the height. Likewise, the surface area of the sphere is 2/3 of the surface area of that same cylinder. This relationship is not only beautiful, it is strikingly exact and mathematically profound. Archimedes was so proud of this discovery that, at his request, a sphere inscribed in a cylinder was engraved upon his tombstone. To reach these results, he used a method that became the ancestor of integral calculus. He mentally sliced a figure into an infinite number of extremely thin sections, compared them with known planar forms, and summed them. He did not possess the formal notions of limit or function, but he understood that one could approach a solution by admitting the idea of infinitely small parts and accounting for them carefully. He applied this method elsewhere, for example, when computing the area of a segment of a parabola or determining centers of gravity of complex bodies. He did not merely solve problems, he devised methods that later formed the basis of formal mathematical analysis. His work, The Method Concerning Mechanical Theorems, addressed to his friend Eratosthenes, is a text unique for the ancient world. In it, Archimedes shows how principles of mechanics can be used to derive geometric truths. He reasons about levers, equilibrium, and moments, not for practical application, but for understanding how form is constituted. For Archimedes, it was important not only to prove, but to comprehend. He was not content simply to use a formula. He wanted to find where it came from. In the treatise, The Sand Reckoner, written as a letter to King Hero, he attempts to estimate how many grains of sand could fit in the universe if one posits its extreme dimensions. To do so, he introduces enormous numbers and describes a system of numeration that goes beyond familiar decimal bounds. This was not merely a mathematical exercise, but an attempt to grasp how to operate with quantities exceeding human intuition. His mathematical works were often accompanied by explanations, schemes, and drawings. He was careful about which problems to publish. It is known that he sent letters to colleagues proposing they solve a problem without immediately revealing his solution. This was not a gesture of arrogance, but an invitation to shared contemplation. Archimedes wished not only to prove himself right, but to prompt others toward their own discovery. Among his other achievements was the approximation of the number pi. Archimedes did not know its exact value, but he calculated with astonishing accuracy that it lies between 3 and 1071 and 3 and 1070ths. That is, between 3 plus 10 over 71 and 3 plus 10 over 70. He did this by inscribing and circumscribing polygons in a circle and increasing the number of their sides to 96. This method demanded immense patience and precision, and he likely carried out these computations by hand, with nothing more than a stick and the sand on his workshop floor. He also studied spirals, cylinders, ellipses, and parabolas. He found areas of curvilinear figures and proved equalities that would not be formally described until the 17th century. His work on spirals shows how deeply he understood movement and form. He could unite geometry with motion, shape with law, theory with mechanics. It is noteworthy that Archimedes did not seek applications for this knowledge. His mathematical writings were not tied to politics or economy. They were an affair of the mind, almost an art. He wrote because he could not do otherwise. He computed because otherwise it would have been wrong. His motivation was neither profit nor fame, but clarity. Later, 1,500 years on, Newton would say that he saw farther because he stood on the shoulders of giants. Archimedes was one of those giants. He gave future generations not merely knowledge, but an approach, to think clearly, to build proofs, to fear no abstraction. Precisely in these chapters of his work, Archimedes left not only formulas, he left a style. He showed that precision is respect for truth, that complexity is not an obstacle but a path, that mathematics is not a set of tools but a way to understand the universe. When the Romans entered Syracuse, the city was exhausted. 2 years of blockade, destruction, and internal strife had sapped its strength. The fortress walls were breached, the garrison partly destroyed, the streets filled with soldiers. According to ancient historians, the commander of the siege, Marcus Claudius Marcellus, forbade his troops to harm Archimedes. He wanted to take the great scholar alive, not for trial or spectacle, but out of respect, and perhaps with the intention of drawing him to Rome's side. Marcellus knew who Archimedes was. He did not need details. It was enough that one man had delayed the Roman army's advance for 2 years, using not weapons, but calculations, not legions, but diagrams. Tradition says he ordered in advance that the old man's life be spared if he were found. But in the first hours of the city's capture, the situation was chaotic. Soldiers looted houses, pursued fugitives, and searched for gold, food, and weapons. In that moment, Archimedes slipped beyond anyone's control. He was at home, not in the forum, not on the city wall, not in a temple, but in his workshop, where he was drawing geometric figures in the sand. It is likely he did not even know that the city had fallen, or knew, but kept working. Archimedes, by all accounts, could withdraw into himself so deeply that he failed to notice what went on around him. When a Roman soldier entered, he did not rise and did not show fear. He made no gesture that could be taken as threat or plea. He simply lifted his head and, without losing composure, said, "Do not disturb my circles." The soldier did not grasp whom he faced. He did not know the old man's name, age, or significance. He saw only an elderly man who did not obey an order, and he killed him, with sword or spear, in a swing or by habit, in a burst or deliberately. The soldier's name is not preserved. The fact of the killing is recorded by several ancient authors. The story diverges only in details. When Marcellus learned that Archimedes was dead, he was, according to Plutarch, shaken. He ordered that the philosopher be buried with honors. He blamed the soldier for a crime against reason. But nothing could be changed. The city had been taken, Archimedes' machine smashed, his workshop plundered. The very man whose mind had awed even his enemies lay slain in the dust of his own courtyard, beside the circles he had so begged not to be touched. There is a view that the words, "Do not disturb my circles," are not merely a request to preserve drawings. They express Archimedes' attitude toward everything occurring. For him, truth, form, and proof stood above politics, wars, and upheavals. He lived in a world of logic where everything has cause and consequence, and where even death is merely a point in a long chain of reasoning. He did not flee or beg for mercy, because in his coordinate system, such actions made no sense. He remained true to himself to the end. A few years later, Marcellus is said to have ordered that Archimedes' grave be marked with a monument depicting a sphere inscribed in a cylinder, in honor of the discovery Archimedes prized most. But, as Cicero claimed 100 years on, the tomb was neglected, overgrown with grass, and only he, a young quester, found it again by clearing away the weeds. Thus, the memory of a man capable of moving the universe with the strength of his thought nearly vanished, if not for the books, the formulas, and that thin line traced in the sand. The death of Archimedes became a symbol of the tragic encounter between reason and brute force. He did not die in battle or fall at a rival's hand. He was struck down at the very moment he was doing what he had done all his life, seeking regularity, drawing, thinking, proving. He was no warrior, yet he was feared. He was no king, yet he was respected. And when he was gone, there remained only silence. A silence in which the voice of one of antiquity's greatest minds disappeared. But that silence was not eternal. Archimedes was remembered and quoted. His works were recopied. He became part of the scientific canon. He entered the conversations of philosophers, the calculations of astronomers, the experiments of physicists. And if on that day in Syracuse a wall fell, on that same day in history there arose a figure no soldier could destroy. Why is Archimedes still read in the 21st century? How did he influence Newton, Galileo, and Leonardo? Is it true that his works were lost and later discovered by chance? After the death of Archimedes, his name did not vanish from the memory of his contemporaries. Already in Rome, despite the circumstances of his death, he was regarded with respect. This is evidenced by the speeches of Cicero, who, by his own words, when serving as a young quaestor in Syracuse, specifically sought out the neglected tomb of Archimedes and restored it. But paradoxically, most of Archimedes' scientific writings for many centuries remained outside of wide circulation. They existed, but they were not copied, not translated, and not included in standard educational programs. The reason lay in the language in which he wrote and the level of reasoning he proposed, both of which were too complex for most readers of the time. Nevertheless, his works did not disappear entirely. Some were preserved in private libraries, monasteries, and collections of Eastern and Byzantine scholars. The Byzantine mathematician Isidore of Miletus, who lived in the 6th century, quoted Archimedes and acknowledged his influence. Arab scholars, particularly Thabit ibn Qurra and al-Biruni, during the Middle Ages studied Greek mathematics and mechanical treatises, including Archimedean ideas. It was precisely through the Arab world that, in the 12th and 13th centuries, Archimedes' works returned to Europe. A turning point came with the discovery of the so-called Archimedes palimpsest, a manuscript that in the 10th century had been copied on parchment, and in the 13th century was erased and overwritten with a prayer book. Only in the 19th century did scholars notice that beneath the layers of religious text lay a more ancient mathematical work. At the beginning of the 20th century, the palimpsest was studied using X-ray fluorescence and other modern techniques. Under the upper layer were fragments of the Method, on floating bodies, and other texts, many of which had previously been unknown in complete form. Thanks to this discovery, it became clear how advanced Archimedes' ideas had been and how far ahead of his time they were. One of those who especially valued Archimedes was Galileo Galilei. He considered him his intellectual teacher, though nearly 2,000 years separated them. Galileo reread his treatises, especially on the equilibrium of planes, and used Archimedean principles in developing his mechanics. He called Archimedes the first to unite theory with observation, and one of the few who truly understood how nature works. Leonardo da Vinci also took an interest in Archimedean inventions. He copied mechanisms, studied diagrams, and tried to reproduce some of the drawings. Although da Vinci rarely cited his sources directly, the structure of his engineering design speaks of deep familiarity with Archimedes' ideas. Levers, gears, water-lifting devices, all of these continued the line that had begun in Syracuse. Sir Isaac Newton, the founder of classical mechanics, likewise acknowledged that his work was in many ways a continuation of the methods laid down by Archimedes. Although Newton already had at his disposal developed forms of calculus based on the concept of the limit and the derivative, the very principle of approximation, the use of infinitesimals, the mental slicing of bodies into parts. All of this Archimedes had practiced long before modern terminology appeared. But perhaps Archimedes' greatest legacy is not in specific formulas or inventions, but in his approach to knowledge. His method of thought, rigorous, logically structured, experimentally grounded, became the foundation of the scientific method. He did not distinguish between pure and applied mathematics. He proved theorems, then built machines upon them. He solved problems, then drew principles from them. He did not divide knowledge into the humanistic and the technical. For him, everything was a single movement of the mind toward clarity. Today, the name of Archimedes is borne by many universities, research centers, and engineering programs. His law is taught in school. His formulas are analyzed in the first years of university study. But far more important is the fact that in every experiment where idea and action, logic and matter, thought and result unite, the Archimedean spirit is present. This is not pathos and not mere homage to history, but recognition. Some ideas truly survive the centuries. Legends have gathered around him. Phrases he may never have spoken and inventions he may never have built are attributed to him. But even if only a part of these stories is true, that is enough to regard Archimedes as a man who truly changed the course of human understanding. And though we do not know every trait of his character, every detail of his life, we know what he left behind. And what he left was, perhaps, the most important thing: a path of thought along which one may still walk thousands of years later. The name of Archimedes outlived his own century. It outlived Syracuse, outlived Rome, outlived entire epochs when it seemed that the world had turned away from reason and science. He left behind no school, no army, no dynasty. He did not conquer territories. He did not raise temples. He did not rule states. But millennia later, he is remembered more often than emperors, philosophers, or generals of his age. Archimedes showed that the world can be understood, that behind the chaos of phenomena lies order, that behind what is visible there is structure. That thought carried through to the end can not only explain, it can create, transform, protect. He was a man who did not seek power, but gained it through precision, who did not chase glory, but became a legend. He wrote no manifestos, took no oaths, spoke no speeches. He sat on the floor, drew circles, and searched for truth, because he could not do otherwise. Every one of his works is not just a collection of formulas, but an act of understanding. He mentally cut figures apart, imagined infinitesimals, gave weight and form to what had not yet existed in the language of his time. He gave us the foundations of hydrostatics, kinematics, and solid geometry. But more importantly, he gave the image of a man who embodied both genius and silence, modesty and depth, the simplicity of a tool and the complexity of a problem. Today his name sounds not like a relic of antiquity, but like a symbol of scientific integrity. In every precise proof, in every engineering drawing, in every school experiment in physics, there is the shadow of Archimedes, not as a mythical hero, but as a reminder. To think is strength, to search is duty, to doubt is the path. And if you have found, do not be afraid to cry out, Eureka.